like to welcome Professor Tomas from South Africa. Over to you, please.
Thank you very much, Safra. So I'll be talking in the next week about Cayley graphs and the degree diameter problem, which is interesting problem in graph theory. So first I will give some simple, I will introduce some simple concepts for maybe those students who are more in combinatorics and not in graph theory on some examples. So let's proceed to the first figure, which is just there. So you can see example of a graph. You can go a little bit down with the graph. No, the opposite direction. Anyway, so the graph which you can see there, it has, so in graph theory, we have vertices and edges. So as you can see on the figure there, we have 8 vertices, and then you can also see edges. So here we have some basic definitions of some basic graph theory terms. So degree of a vertex is the number of vertices adjacent to the vertex, or the number of edges incident to a vertex. So again, vertices are those like those. So again, if you can come a little bit down with the figure, because you need to know if this will work during the lecture or not. Maybe if it doesn't work, sometimes can help. Maximum distance between two vertices. The maximum or the furthest doesn't mean that you are going the furthest path. You are always going in the shortest possible way, but you are looking for two vertices which are furthest from each other. If at some stage something will be unclear and you will be worried that you will be not able to follow the whole lecture, you can stop me even during my lecture. You don't have to wait till the end and then ask me only afterwards. Okay, so we can continue. So we introduce degree. We also introduce the distance and also the diameter. And now we are in the next figure. Maybe you can just keep it. So as you could see in the previous figure, it was just a graph having, I think, 8 vertices. Now, for example, in this figure, I'm illustrating a graph which has general number of vertices, which is n vertices or n nodes of a network. Because here we have n minus 5, and here we have 5 more vertices. And the distances, and here I am also mentioning degree and distance and diameter, but it's again quite obvious because the degree of these vertices will be 1. As you can see, each of them is connected only to this vertex. Degree is 1, degree is 1, also this one. Well, the degree of this one will be 4. What do you think would be the degree of this one? Yes, it's connected to all the other vertices in the graph, so the degree of it is n minus 1. What do you think is the diameter of this graph? Are there any 2 vertices whose distance is 3? No. There are no 2 vertices whose distance is 3, because from any vertex to any vertex, you can get via this vertex, right? So the diameter of this graph is 2, because there are many vertices whose distance is 2. Great. So it seems like we are very comfortable with degree and diameter. So we can proceed. So as we already talked about degree, we already mentioned distance, we already mentioned diameter, and great. And now I guess we need to make it a bit smaller because we can't see that there. Great. So degree diameter problem. And you have here some motivation. But suppose we want to set up a network in which each node has a limited number of connections to other nodes. Okay? So that's one parameter, one condition. Each node has a limited number of connections to the other nodes. And the second parameter, that any 2 nodes will communicate by a route of limited length. Why is this useful? Because if we want to have some large networks, we can slightly proceed. So if we want to have some large network, we are limited. Let's say we have 1 million computers in the network. We cannot connect one computer to 999,000 of the other computers, right? And also if we have 1 million computers, the network wouldn't be efficient if you connect First one is the second one is the third one is the fourth one, and so on. So you want any two nodes in the network to be relatively close. That's the diameter. Any two nodes in a network to be relatively close. And the second parameter is the degree. You're one computer in a network, you cannot connect it with so many. You are again limited. And this is the second parameter, which is called the degree. And this problem can be translated into graph theory because we are looking for the largest graph, or the problem is to find the largest possible number of vertices in a graph which satisfy those two parameters. So this problem might seem quite theoretical, but actually last year Intel from USA contacted me regarding this problem because they were actually looking for the best results which are known for diameter 2. So they were constructing some networks where they wanted to have diameter 2, which means every computer from every computer is of distance at most 2, and the degree can be general. So actually the application of this problem is in any network design problem. It can be telecommunication network, it can be computer network. So you have two limitations, you have D and K. Obviously the best is to study in general, but it's also possible to study it for particular values. Let's say you will study it for diameter 7 and degree 5. And the question is, how many at most nodes in a network for the limited two parameters you can construct? Okay, we can stop here. And here is the question for just one particular problem. Let's just look at very small values. And how would we answer just this simple problem for the two particular values? So how many computers can we have in a network which has the following two conditions? Every computer can be connected with at most 3 other computers. So let me just illustrate it. If you have any computer in a network, any computer can be connected with at most 3. And the second condition, there is either direct connection between any two computers, means direct connection. If you pick any two computers, either they are connected by an edge, or there is a connection through at most one other computer, which means the diameter is 2, right? So if these two are not connected, they are connected by one more. So this means we are looking for the largest possible graph of diameter 2 and degree 3. Well, equivalent question we could translate to graph theory. Find a graph of maximum degree 3 and diameter 2, having the largest possible number of vertices. But why we are saying maximum degree 3 and not necessarily degree 3? Because degree, every vertex has different degree, and sometimes if you construct some graph, it's not necessarily possible to have always the same degree 3. So let's say maximum degree 3 means you will allow yourself to have degree at most 3 for every vertex. But sometimes it can happen that all the vertices will be having degree 3, but one of them will have still degree 2. So you can't satisfy the maximum degree to be 3 for every vertex. And this is the answer of the problem. Here, if we go slightly down, you will see the whole graph, which is the largest possible graph, which is actually called Petersen graph for these two parameters. If you look at this graph, really the degree of every vertex is 3. Every vertex is connected to 3 other vertices. And again, if you check carefully, the diameter of this graph is 2. There are no 2 vertices whose distance is 3. So the distance between every 2 vertices is actually 1 or 2. For example, these 2 vertices are connected via this vertex. These 2 vertices are connected via this vertex. And so on. So this is the simple solution when one parameter is 3 and another parameter is 2. Before we proceed to the next page, let me give even an easier example. If the degree would be 2, we don't have to show more. And the diameter is 2. What is the answer? Actually, somebody that wants to show us more. So you already could see what is the answer. So if the degree is 2 and the diameter is 2, the problem is even easier. Find the largest graph having degree 2. And now, since both parameters, degree and diameter, start with D, it will be slightly confusing because we must choose a different letter for one of them, right? So usually we are using, for degree, we are using D, and for diameter, we are using K. So also try to remember, degree will be D, that's the one number of connections, and the diameter will be K. That's the furthest distance between any two vertices. So the largest graph for parameters 2 and 2 will be 5. Let's look at this graph. So as you can see, really it's clear that the degree is 2 because as you can see, every vertex is connected to the two other. And now diameter. I guess it's also quite easy to see the diameter is really 2 because any two vertices, you can get there by 2 steps. You might be wondering, let's say these two are of distance 2, but what about these two? Obviously, you are not going this way. That wouldn't be distance. The distance between two vertices is going the quickest possible way. So that will give you this route from this vertex to this vertex. It will give you this route. So it will be this graph will have diameter 2. We can proceed to the next one. Good. Now, this is the definition of the degree diameter problem. Determine the largest possible number of vertices in a graph of given maximum degree D and diameter K. So this is generally stated problem for general D and K, which is mentioned here. Now, obviously, it's difficult to study the problem in general. So how do we study the problem? Often we study the problem that we fixed one parameter, or if even we just really want to focus on finding something, some very specific value, you can fix both. Let's say you will fix D to be whatever 7 and K to be 9. And actually for small values, as maybe you can guess, the best way to find large graphs is searching by computers. But the computers will be able to overtake mathematical proofs or mathematical strategies only for small values. Let's say if D and K are very small. But already, if one of them is going to infinity, then actually mathematicians are usually able to find stronger results than computer scientists. So computer scientists usually find the best possible results for small values because they can use programs and strategies to look for the largest possible graphs for, let's say, small D and K. If one is going to infinity or is very large, the number of vertices actually is really growing enormously. As you can see here in the Moore bound, so the Moore bound is actually the upper bound, which is telling us there is no way to find more vertices than the number of vertices which is mentioned here. So let's say if we can still keep it there. So if we are looking for, let's say, if we denote the largest in a graph theory, often for the number of vertices, we are using n. Number of vertices or order of a graph is denoted by n, and we are looking for n in terms of D and K. So let me put it as a lower subscript. So n dk will be the largest number of vertices in a graph of degree and diameter. Still, we are here in the Moore bound, and y, actually we cannot get more vertices than this one. So let me just illustrate this on some kind of a diagram here, what I'm going to include here. So let's say you take any vertex. This vertex is adjacent to at most the others because we mentioned D is the degree, D is the degree, and K is the diameter. Okay, and we want to find the largest possible number of vertices. So one vertex obviously can't be connected to more than D vertices because the maximum degree is D. Okay, so let's just make him adjacent to D vertices. So we will have here one vertex at the beginning, and then one vertex is connected to the others. And now this one, in the next level, it can be connected to at most how many vertices? It's already connected to one there, right? So it can be connected to at most d minus 1. And what about this one? It can be connected to at most how many? Same, to at most d minus 1, because it's already connected to 1. So again, to at most d minus 1. So how many vertices we will have in the second level? D times d minus 1, right? And now you can see how it actually works if you look at this bound, because it continues. Then this vertex is already connected to 1. In the next level, let's say, if we want to have the graph of diameter 2, then you would have to stop here. But obviously, also assume we are looking for the largest possible graph of diameter 2. Well, from this level, you can't go further anymore because it will be diameter 3. But now you will have many vertices in this level. And now the challenge would be, can you start connecting these vertices somehow between themselves in such great way that you will really be able to achieve this bound? Actually, it's almost never possible. So it's not possible to get a graph which has the maximum possible number of vertices unless it's some trivial case. So this bound which we have here is actually in most cases not achievable. So it's really only theoretical bound. Maybe you can also see, so if you would be going to the third level, as you can see in the second level, you have d times d minus 1 vertex. Well, in the next level, you would be again connecting each of them with d minus 1. Therefore, the next level, you would have d times d minus 1 squared, right? So if the diameter would be 3, then the number of vertices, which is the theoretical maximum, would be 1 vertex at the beginning, plus hopefully d vertices in the first step, plus hopefully d times d minus 1 in the second step, plus, and hopefully d times d minus 1 squared in the third level. But again, this is only theoretical maximum. You would never be able to connect them in such a way that it would actually work nicely and you would get the graph with this number of vertices. Actually, this problem, degree diameter problem, is quite famous problem. So in case you Google it, you will also find the Wikipedia page and many other sources with the largest graphs, at least for the small values. Or let's say DNK being at most 15. Obviously, for large values, there is also competition. Let's say somebody will pick degree to be 2 or degree to be 3 or diameter to be 2 and 3, and the other one being infinitely many values, and try to solve or find the largest possible graph. So there are two ways we can still keep here. So there are two ways how we study this problem. Me and my research, and actually most people who study the degree diameter problem are trying to find lower bounds. So there are lower bounds and upper bounds. NDK, the largest possible number of vertices for given, for given DNK, for given degree and diameter. So in most cases, it's unknown. What is the largest possible order? So we are looking for lower bounds and upper bounds. Lower bound will be a construction. Once we construct a large graph, let's say from 7 and 9, with some number of vertices, we are recordable. And then maybe after 2 years, somebody will overtake us and construct a graph which has actually more vertices than the one which we construct. So this is the lower bound. Once you find the graph, it exists, is a lower bound for NDK. On the other hand, there are upper bounds for loops of non-existence. So if you can theoretically prove that the graph which has this number of vertices, it's impossible to find. So let's say this Moore graph, Moore bound often has notation MDK. So MDK, so number of vertices of a graph with given degree and diameter is at most MDK, which is the Moore bound. But if we prove that there is no way for certain DNK to reach the Moore bound, then we actually prove that NDK is smaller than MDK. And then we can take it from there. Again, for some values, we can prove that even MDK minus 1 is impossible. And it will be NDK is at most MDK, let's say, minus 1. and so on. So there are also researchers which are actually trying to push this bound down. And actually, researchers who studied this degree diameter problem from the other side, from the upper bounds, are former maybe students and collaborator of Mirka Miller, which is a mathematician who was working in Australia, and also actually Indonesians are a little bit active in the upper bound. Okay, so now Moore graphs. What are Moore graphs? Also very famous graphs in graph theory, Moore graphs. This name is quite famous. So they are extremely unique. So let's just mention those few cases where we can construct a graph reaching this bound, which we have here and which was presented in the next page. So Moore graphs are very rare, and the Moore graphs we can still, for maybe next 10 minutes, to stay here. So the number of vertices in a Moore graph is equal to the Moore bound. Therefore, it's called Moore graph. So which are these graphs? Complete graphs. So in graph theory, I guess most of you know, complete graph is the graph where every vertex is connected to every other vertex, right? So for example, if we take complete graph is 5 vertices, why is it a Moore graph? Okay, so let's look here. Complete graph with d plus 1 vertices. So in graph theory, notation for complete graph is capital K, and this is the number of vertices. So in general, Kn, you know probably quite well, Kn is a complete graph of n vertices. So if the complete graph has d plus 1 vertices, degree plus 1, that is the actually Moore graph for diameter 1. You know that the complete graph has diameter 1, right? Because every vertex is connected with every other. So the complete graph has diameter 1. What about the degree? As you can see, let's say if the degree in here, the degree is 4, so it will be complete graph is 5 vertices. So in general, if the degree would be d, it means the complete graph has d plus 1 vertices. So those are the first class of Moore graphs. Then the next set of graphs is cycles with 2k plus 1 vertices. You might be wondering why 2k plus 1? What does it actually mean? It means odd cycles. Cycles with odd number of vertices. Again, the representation of C in graph theory, we are using C, capital C for cycles. So let's say Cn represents cycle with n vertices. And even if I didn't define it yet, I guess you can correctly assume what is a cycle. So a cycle is just a graph which has this kind of structure. So it will be every vertex has this 2. Therefore, as you can see, there are cycles are Moore graphs for degree equal to 2 and for general diameter. So diameter is general. So let's say the one which I have here has 1, 2, 3, 4, 5, 6, 7 vertices. So n is equals to 7. Can you tell me what is the diameter of this graph? The diameter. Well, what is the distance between this vertex and this vertex? The distance between these two is 3. Are there any two vertices which are further? No, there are no two vertices which are further from each other. The distance is 3. So actually the diameter of this graph is 3. And as you can see, the number of vertices is 2k plus 1. Since the diameter is 3, the number of vertices will be 2k plus 1. So for given diameter k, cycles have 2k plus 1 vertices, and those form the other set of Moore graphs. And then this one is actually just one graph, which was already presented before. Petersen graph is the Moore graph for k is equals to 2 and d is equals to 3. We can even check if it really satisfies the bound, because k equals to 2, what does it mean? It means diameter is 2. So here we have the bound, we would have to stop here, right? because the diameter is 2. So in case degree is 3, so not general, here we have general. One is adjacent to the others. If one is connected only to 3 vertices, it means each of these can be connected to 2 vertices. And in the last step, actually in this special example, it will work. It's possible to connect these vertices in such a way that all of them will have degree 3, and any 2 vertices in a graph will be of distance at most 2. So the diameter is 2. Maybe you can try it by yourself as an exercise, and you will see maybe it will take you a bit of time to connect these vertices in such a way to get graph of degree 3 and diameter 2. And actually this graph in graph theory we call isomorphic if it has the same structure. And this graph which you are going to construct we can rewrite it in this way, which is Petersen graph, which was presented before. So if you connect it correctly, the graph which you will get here is the same graph as the Petersen. And then we have Hoffman-Singleton graph, which is the graph for diameter 2 and degree 7. Maybe you can think and you can maybe tell me what you think. How many vertices has Hoffman-Singleton graph? If you want to know the number of vertices of Hoffman-Singleton graph, you can again take it from here, because you will just replace the diameter is already replaced. So the diameter equals to 2. That already replaced inside the Moore bound, which was presented in the next page, because this is Moore bound for graphs of diameter 2. And the degree, well, you will just replace degree by 7. So if you replace this degree by 7, you will find out that this graph has 50 vertices. So this is another Moore graph. And it might be quite surprising. It's proved for every other case, for every other combination of V and K, that the Moore graph doesn't exist. Except for one case, which seems so strange. Why diameter 2 and degree 57 for this one particular case, it's still unknown if the Moore graph exists. We still don't know if it's possible to construct a graph with, and this problem has been studied for decades, and still it's unknown if we can construct a graph of diameter 2 having 1 plus our degree is 57 plus 57 and plus d times d minus 1, which is 57 times 56 vertices. This one is unknown. If this can be constructed, we can slightly proceed. And I just already mentioned actually this one. And then if we count, we can slightly go down if it's still possible to see the next one. So it's fine. So we can actually count the number of vertices to see that actually Hoffman-Singleton graph really has 50 vertices. What was already mentioned here, I just mentioned it also in this case. And in the next figure, which is mentioned there, I'm just going to check if you were listening or following carefully. Is this graph a Moore graph or not? It's a cycle with 8 vertices. And we are asking, so if degree is 2, let's just think, what is the diameter of this graph? The diameter is 4. And we are asking if this graph is a Moore graph, or if we can find a graph for d equals to 2 and k equals to 4 with larger number of vertices. Can we have more than 8, or 8 is maximum possible? Exactly. So this is not a Moore graph. There is a graph which has more vertices for diameter 4 and for degree 2. And the answer is a graph with 9 vertices, and it will be cycle C9. So cycle is 9 vertices, not 8. 8 vertices, not a Moore graph. Okay, we can proceed. Next one. Great. Okay, now we are starting with automorphism of a graph. So, what is automorphism of a graph? An automorphism of a graph is a permutation of vertices which has the property that UV is an edge. If you are unsure what UV means, usually U and V we are using for notation of vertices. So if you are taking vertices UV, then UV is edge. So let me just illustrate it just for those which are by chance not students in graph theory. So if notation for this vertex is U and notation of this vertex is V, then the notation for this edge is UV. Okay? So edge UV. So UV is edge if and only if PUPV is an edge. So we can again stop here because I want to give a few examples because I don't want to lose some students here in case it's unclear what is an automorphism. So, so if we take, for example, graph, which is this one. So let me have vertices, let's say U1, U2, U3, U4, and if possible, we can have the definition in the back, so we can proceed to the next page. Good, we can stop here. So again, automorphism of a graph is permutation of vertices, which has the property that U is an edge if PUPV is an edge. So I'm asking, is there an automorphism which can carry this vertex to this place? That's the first question. And the second question, is there an automorphism which can carry this vertex to this place? So the question is, I want to put U1 here. Can I rewrite the vertices now in such a way that each of them which are adjacent here will be adjacent here? Well, I guess it's quite clear that I can just reach these two, right? So if I put here U1 to this place and U3 to this place, so this will be my permutation. So then the image of U1 will be here and the image of U3 will be here. Then this one works. You can keep this, right? But if I am trying to do it, if I'm going to answer the other question, there is no automorphism which can carry this vertex to this place. So if I have the same graph, and I'm asking, can I have an automorphism which carries this vertex to this place? Well, if you want to put U1 here, automorphism is a permutation of vertices such that U is an edge if only in the image PUPV will be the edge. So since U1 was adjacent here to U4, U3, and U2, can you somehow put here U2, U3, U4 in such a way that U1 will be adjacent to those three? You can't, right? Because as you can see, U1 is adjacent here only to 2. So it gives you actually the property that if it's automorphism, it means, which is probably mentioned here, we can go slightly down. If a vertex has the image, again, if a vertex of a graph and if the P is the automorphism, then the image has the same degree. So in the graph, in the next graph, the degree of a vertex must be the same as in the original graph. So you can't have a permutation where you are having here degree of U1 being 3, and here degree of U1 is 2. So it's not possible. Okay, now let me just mention this one. Every permutation of the vertices of complete graph is an automorphism. Because if you take a complete graph, let's say, which has vertices u1, u2, u3, u4, u5, and now you will take some permutation. So let's say in the next graph, we will have p u1. Let's say u1 will go to u4. P u2, u2, let's keep it where it is. U2 will stay u2. P u3, let's put u3 to, let's say, u1. Whatever, you can p u4 and p u5. So obviously you can pick any permutation and it will still be the same graph because every vertex is connected to every vertex. So however you change the order, still the u1 will be definitely adjacent to all the others. U2 will be still definitely adjacent to all the others, and so on. So every change of the order of the vertices will again just give you the same graph. And now the next property. If you are and we are the vertices and P is an automorphism, then the distance between UV will be the same as the distance in the new graph, right? Because again, this property is quite simple. It's also preserved distances. So automorphism will again preserve distances. So if the two vertices, let's say, if I have this graph, the distance between these two vertices is 2. So even if you take some automorphism of the graph, the distance between the new vertices which are representing u4 and u2 will be still 2. Well, this graph is quite simple, so it's obvious. But even if it's very complicated graph, and the distance between u and v is, let's say, 10, then if you take automorphism of the graph, so the distance between wherever u and v go, the distance will be again 10 between them. Okay. Now we can just stop here at the vertex-transitive graph. So vertex-transitive graph is defined with the help of automorphism. So G is vertex-transitive if for every pair of vertices there is an automorphism G that carries U to V. So for every pair of vertices, there must be automorphism which carries one vertex to the other. So do you think this graph which is mentioned here, is it vertex transitive or no? No, because there is no automorphism which carries this vertex to this vertex, as we mentioned. You might be arguing and say, no, but there is automorphism which carries this vertex to this vertex. Or there is automorphism which carries this vertex to this vertex. But as you can see, the graph is vertex transitive if for every pair of vertices. So you can pick any two of them, and there must be automorphism carrying one to the other. But there is no automorphism which carries this vertex to this, right? Therefore, this graph is not vertex transitive. And now the Petersen graph is vertex transitive. So what does it mean? The Petersen graph actually, it's written here. Just let me slightly correct this part. And maybe you might be wondering if there is really automorphism. So since Petersen graph is vertex transitive, it means there is an automorphism which carries, for example, this vertex to this vertex. Let's just double check. So what about having vertices? Let's say this one will be u1, u2, u3, u4, u5, and let's have this one to be v1, v2, V3, V4, V5. So obviously you can see if you will be just, let's say, can we go with V1 to this place, or can we go with V1 to this place? Then you can probably see that one will work. But what about going with V1, let's say, to this place? So let's just illustrate that it will really work. So we can just put V1 even to the kind of the part which looks like a star. Okay, so if we have this graph, and I'm asking, can we now put V1 to this place? And can we make the names of the other vertices, again, V2 up to V5 and U1 up to V5, in such a way that every vertex, every two vertices which are adjacent here will be adjacent also here? Well, it will work. Look, V1 is adjacent to V2. So let's go now like this. V2, V3, V4, V5. And now, as you can see, V1 is adjacent to U1, V2 is to U2, V3 to U3. So now V1 is to U1, V2 is to U2, V3 is to adjacent to U3, V4 is adjacent to U4, and V5 is adjacent to U5. And let's look what was happening here. U1 was to U3, U3 to U5, U1, U3, U3, U5, and so on. So as you can see, that is really for any two vertices. Well, I just picked one combination, but for any two vertices, there is an automorphism which can carry one vertex to any other. Therefore, this graph is vertex-transitive. Now, H-transitive. So, very similar definition to the vertex-transitive. Just H-transitive will be a graph if for any pair of edges there is an automorphism which can carry H, one H to the other. And again, maybe a good example to illustrate the difference between vertex transitivity and H transitivity is the set of complete bipartite graphs. Maybe good, we can stop here. So now, the complete bipartite graph. Again, maybe not sure if all of you know what is the complete bipartite graph. So let me just illustrate it. So let's just take some small number. Let's say here we have in general K, N1, N2. So let's just have it something like K to 3. K to 3 means you have two partite classes. First one has two vertices, and the second one is three vertices. And the complete means everything from one side will be adjacent to everything on the other side. So here we have complete bipartite graph, means every vertex from one partite set is adjacent to everything on the other partite set, but nothing in the same partite set is adjacent. And now look at this graph. So here we have two vertices in this partite graph, three vertices. And now, is this graph vertex or H transitive? Well, the question is answered there, but it should be clear from what was mentioned before why it is not vertex transitive. Because if you pick this vertex, is there an automorphism which can carry this vertex to this vertex? That one, yes, because actually you don't have to do anything with this vertex, right? So we find you have U1, U2, V1, V2, V3. If you just switch U1 and U2, then every vertex, let's say U1 is adjacent to V1, V2, V3. If you switch these two, it still will be the same graph, right? Because here U1 will be also adjacent to V1, V2, V3. So you can switch V1 and U2, U1 and U2, but can you put, let's say, this vertex to this place? Yeah, that will not be an automorphism because here U2 was adjacent to 3 vertices, but obviously if you put U2 to this place, it would be adjacent only to 2 vertices. So it cannot be an automorphism. Now we know that this graph is not vertex transitive because this vertex cannot go to this place. But this graph is edge transitive because any edge can go to any other place. So let's just again illustrate it. Why this edge transitive? Now we are focusing on edges. So let's give names to edges. So it's not vertex transitive, but if we have, so now since we are focusing on edges, let's just have this one to be. Let me think about some good way to write names, maybe E11, E12, E13, and this one will be E21. This one will be E22, and this one will be E23. And now I'm asking, is there automorphism which carries this edge? Well, I'm just going to show it on just some 2 edges, but it will work for actually any combination which you will take. So can this edge, let's say, go to this place? And again, you will easily find yes, because this edge can go to this place. Let's just illustrate it. So here we have E12 in this place. Let's put it here, E12. Well, E12 was incident with E13 and E11. No problem. We will not have to put them nicely here, E11. We can put here E11. And the next one, E13. And here E12. E12 was having again common vertex with E22. So since E12 had a common vertex with E22, let's put here E22. So E22 must come to this place. There is no other way. E22 must come here. And now E22 or let's say, I think here actually we can go again in any way. So E22, E21, E23. E21 actually we can't go in anywhere, but this will work. E23. So again, you can check any 2 edges which are incident here are incident also in the next graph. So the graph is edge transitive. If for any pair of edges there is an automorphism which carries one to the other, but it must work for any 2 edges in a graph. Therefore, this graph is edge transitive, but not vertex transitive unless, now why unless n1 equals to n2? What will be the difference if we have, let's say, K33? Because what that unless means, like what is going to happen if we have a complete bipartite graph K33? So this is the graph. So can you tell me what is the difference? So that unless, does it mean that in this case it's not edge transitive, or does it mean that in this case it is vertex transitive? Because if n1 is equals to n2, it's vertex transitive. Yes, it is also vertex transitive and also edge transitive. So if n1 is equals to n2, then the graph is also vertex transitive and also edge transitive. So there will be an automorphism. So I'm going to just tell you why it is vertex transitive. It is vertex transitive because there is an automorphism which carries this vertex to any other vertex. It is also automorphism which can carry this vertex to the vertices on the other side. And then again, you can give names in such way that again, the vertices which were adjacent in the original graph will be adjacent also in the new graph. I don't want to start with a new concept now. So for today, we will stop here and we will start with Cayley graphs tomorrow. Not sure if there is some question part.
Any question from the audience? Vertex transitive graph must be regular.
Yes. The vertex. No, not regular. Yes, the vertex transitive graph must be regular.
N1 is equal to N2. That means if there is.
Yes, in general, vertex transitive graphs are subsets of regular graphs.
I have one question. When we are finding this, the largest graph with maximum given degree and diameter, do we are requiring any conditions on the number of edges? I mean the size.
That comes directly from the degree.
Yeah.
Because the number of edges and maybe stated degree. So yes, so it's kind of related to the degree of a vertex.
Oh.
You said cycle graph of odd number of vertices or is
Not Moore graph. Okay, let me just. Yes.
Of the number of vertices is odd.
Odd cycle.
Odd cycle.
Yes.
They are more graph.
Yes.
And, what about the cycle graph of number of vertices? Odd, even.
Even. Yes. So those are not Moore graphs. Okay. In general.
But it can be some of them.
You mean the even ones?
Even.
No, the evens unfortunately will never be. The problem is they will be always overtaken by the odd ones. Because if you take even one, any even which you take, let's say let's take cycle with 100 vertices. Okay? So it's even, okay? So we have cycle with 100 vertices. And what is the degree here in this case? What is the degree of every vertex? Okay. Degree is 2. What is the diameter? What do you think of cycle with 100 vertices? Well, let me pick this vertex and the vertex furthest from this vertex. Which one is furthest? Somewhere completely on the other side, right? What is the distance between them? 50, right? So maybe this one you must remember that maybe in some sense you are guessing, what about 99, right? Because you can think about like maybe there is 99 edges going around. But that's how you don't want to reach this vertex from this vertex going this way. Let's say if these are the streets and I tell you go from this town or this town to this town. Obviously you are going this way, right? You are not going to go via 998 other towns. You are just going this way, right? So the distance is the quickest way to get there. And you will not find two vertices whose distance is more than 50, okay? Therefore, the diameter of this graph is 50. Because pick any two vertices, there will be a root using at most 50 edges, okay? But now, if this graph would be a Moore graph is the largest, okay? But the largest for k equals 50 and for d equals 2 is not this graph. Because it can be overtaken by which graph?
101.
By 101. Because if you add one more there, it will have the same parameters, but it's bigger. Therefore, cycle with 101 vertices is a Moore graph because it overtook by one the graph which has 100 vertices. And maybe also the other way, how you can check if that is not a Moore graph is to use the bound, because the Moore graph will have the number of vertices 1 plus d times d minus 1 plus plus d times d minus 1 to k minus 1, right? And now if you replace k 50 and d2 to this one, the number which you will get will be 101, which means this is the largest possible. 101 vertices, not one.